Okay, here are the solutions to the 1998 multiple choice. This is the no calculator part. I'll start with number one and we'll see how far we get with the first video here. Number one, what's the x-coordinate of the point of inflection of the graph? Well, to find a point of inflection, we're looking for where the second derivative is equal to 0. So, first derivative of this would be the 3 and then 1/3 would cancel out. It would be x squared plus 10x, and the 24 goes away. The second derivative would be 2x plus 10, setting that equal to 0. We get x is equal to -5. And it's just a polynomial, so they're looking at the answers. We don't actually have to do the number line. If it were a more complicated function with like an e to the x or something like that, we might have to do the number line, but this is just a polynomial, so we know that it's actually going to be at -5. Number two, graph of a piecewise linear function. What is the value of this derivative? Well, let's see. Since it's a geometric looking thing, we can find it just by doing area. -1 to 4. This is going to be positive area here and negative area here. So let's see. This triangle, that's a 1/2 triangle, so that has an area of 1. That's a 1/2 rectangle, has an area of 2. That's the same triangle. This is a 1/1 triangle, so that has an area of 1/2, and this has an area of 1. So I've got positive 4 area minus 1.5. That gives me an area of 2.5. That'll be B. Notice that the area, if you forgot to make this negative, that answer is there. That area below the x-axis is negative. Okay, and then this one, this looks like just a regular integral. That's the same as x to the -2. The antiderivative of x to the -2, we bump the exponent up 1 and divide by the new exponent. That gives me that. I'm going to bring the negative sign to the outside. Plug in the 2 in there. 2 to the -1 is 1/2, minus 1 to the -1 is 1. That's -1/2, negative. Be careful with the sign here. The sign mistake answer is there, so just watch out for that. You could also think to yourself, the graph of 1 over x squared looks something like this from 1 to 2, so it's got to be positive area, so that can't be right. Number 4, if f is continuous on this interval from a to b and differentiable from a to b, which of the following could be false? Well, this is a strong condition, right? If it's continuous and differentiable. So what does this say? That f prime of c is equal to, this is the average rate of change, and this is the derivative for some c. That's the mean value theorem. And the mean value theorem does hold if it's differentiable. So that's true. F prime of c equals 0 for some c. Does it have to, that would be like it has a maximum or a minimum or a saddle point. And I don't think anything that they told us here necessitates that. So I think this could be false. Let's check the other ones. Does f have a minimum value here? It does, because it's a closed interval. So even if it was always increasing or decreasing, that minimum would be at the end point. And likewise, it would also have a maximum value. Functions have to have maximums or minimums on closed intervals if they're continuous. And does the area under it exist? It does. It only needs to be continuous for that to be true. So those are all true, and B is false. It doesn't have to have a horizontal tangent line. Okay. What's the area from 0 to x? Sine x, well, let's see. The antiderivative of sine is negative cosine x. I should put t here because we're using the x here, from x to 0, so that's negative cosine of x. Actually, I'm going to bring that negative to the outside so I don't make a sign mistake. Minus the cosine of 0. Cosine of 0 is 1, so that's negative cosine x plus 1, which is equivalent to this, e. Number 6, it looks like we've got y's in here, so it looks like they're going to be implicit differentiation. So let's find the derivative. I might need a little more paper here. So this is number 6. The derivative of x squared is 2x. The derivative of xy, I've got to use the product rule. It's the derivative of the first times the second plus the first times the derivative of the second equal to 0. So dy dx, doing a little algebra here, it looks like it would be minus 2x minus y, and then divide by the x. Now there's a y in here, so I need to figure out what y is. So plugging 2 into the original here, 2 squared is 4 plus 2 times y equals 10. So when x is 2, y must be equal to 3. So plugging 2 and 3 in here gives me negative 2 times 2 minus y, which is 3, all over x, which is 2. That's negative 4 minus 3. It's negative 7 halves. That's answer A. Number 7. This is one of those integrals where if we just divide through by the x, that's going to make things a lot easier here. So there's only one thing in the denominator. So x squared divided by x is x minus 1 over x. The antiderivative of x is x squared over 2. The antiderivative of 1 over x is natural log x, from 1 to e. Now that's e squared over 2 minus the natural log of e is 1, minus 1 over 2, I'm putting the 1 in now, minus the natural log of 1 is 0. So that looks like e squared over 2 minus 1 minus a half. That's the same as answer choice E. Number 8. Let f and g be differentiable functions with the following properties. The g function is greater than 0 for all x, so it's above the x-axis, and f of 0 is equal to 1. So if this function, if the h function is the product of those two, and h prime is f of x times g prime of x, then f of x must be, well, let's see, the derivative of the h function using the product rule would be f prime of x times the derivative of the first times the second plus the first times the derivative of the second. And they're telling us here that h prime of x is only equal to this. So that means this must be equal to 0. So let's see. This is not equal to 0. This can't be equal to 0 because they told us that right there. Hold on one second. Sorry about that. Phone was ringing, but it's not an important call. Okay, so this must be equal to 0. That means since this can't be 0, then f of x, let's see, must be equal to a constant function, right? If it's going to be 0 all the time, because we know that this is not making it 0, because that's that. And since f of 0 equals 1 and it's a constant function, it's got to be just that constant function 1. Right? That's the only way that this is going to be equal to 0. All right. Number 9. Let's see. The flow of oil. So this is a derivative, right? Ours. Of the following, which best approximates the total number of barrels? Well, this is a situation, if this is barrels per hour, and this is hours. To get barrels, you multiply this times this, right? Which means we're looking for an area here. Area is multiplying, if you think about like a rectangle, height or length times width, right? So multiplying this times this gives us barrels. So approximating the area here, this is 6 by 100, so that's about, each one of these boxes is about 600. And these are more or less half of that, so that's about 300 and 300. So that's 600, that's like 5 600s, so that's about 3,000. It's generally a good way of thinking about these things, like whether you should be taking a derivative or an integral if you look at the units. Since we're looking for total number of barrels, how do you get that from these units? You multiply them, and if you're multiplying the units, it means you're taking an integral. If we were looking for, if we found a slope here, that would be barrels per hour, right? That would be something else. Okay. What's the instantaneous rate of change at x equals 2 of this function? Well, instantaneous rate of change just means derivative. So, I'll give myself a little bit of room here. Looks like we're going to have to do the quotient rule. So the derivative of this function is low d high minus high d low is just 1 over low low. And plugging 2 into that, I get 2 minus 1 is 1 times 4 minus 2 squared is 4 minus 2 is 2 over 2 minus 1 squared, so that's 2, or d. Number 11, if f is a linear function and a is less than b and they're both greater than 0, then the area from here to here of the second derivative, well, let's see, if f is a linear function of the form like mx plus, I'm going to use k instead of b since b means something else here, then the first derivative of that would just be the slope, and the second derivative would be 0. So this is like asking what's the area under the line 0, and there's no area under that at all. It's just, it is the x-axis. So from a to b, the area would just be 0. Number 12, and notice that's true for any linear function. It doesn't matter what the slope and y-intercept are. By the time you take the second derivative, they're both gone. Number 12, we've got a piecewise function. It's the natural log function from 0 to 2, and then at 2 it changes over to being x squared times the natural log of 2. And they want to know what's the limit as x approaches 2. Well, if these two things approach the same thing, then it's whatever that is. But if they don't, then the limit doesn't exist. So let's plug 2 into these and see. If I plug 2 in here, I get natural log 2. And if I plug 2 in here, I get 4 times the natural log of 2. So it's not approaching the same thing, which means the limit does not exist. The limit does not exist. Number 13. The graph of the function f is shown above and has a vertical tangent at the point 2, 0. There's a vertical tangent line, so the slope would be undefined there. And horizontal tangents at here and here, just like it looks. For what values is f not differentiable? Well, it's not differentiable here. It's not differentiable here because it's vertical. And that's it, right? 0 and 2. I mean, 1, certainly 1 and 3 are no problem, right? Those, it's differentiable, it just has a derivative of 0. Well, 0 and 2 are the problems. I guess maybe this could be a popular wrong choice, thinking that it's only the spot where it's not continuous, but it's not differentiable here either because you'd have an undefined slope. All right, next one. A particle moves along the x-axis, so its position is given by this. For what value is the velocity 0? Well, velocity is the derivative of position, and that would be equal to 0 at 3. If the f function is equal to this, then f prime of 2, well, the derivative of a function defined in terms of an integral, it just turns into the x just drops in, so that's just equal to x cubed plus 1. And if we plug 2 into that, we get 2 cubed is 8 plus 1, the square root of that is 3. Number 16, if f of x is equal to this, then the derivative is, that looks like maybe 2 layers of chain rule. So the derivative of sine is cosine of whatever times the derivative of what's inside. Derivative of what's inside is the derivative of e to the whatever is e to the whatever times, since that's not just an x, we have to multiply by the derivative of that, which is negative 1. So that'd be negative cosine of e to the negative x. No. Times, it looks like this. That's the same. That's what we have. I think we've seen this one before. Graph of a twice differentiable function, which just means you can find the first and second derivatives, is shown. Which of the following is true? Well, let's see. F of 1 is 0. The derivative at 1, since it's increasing, is positive. And the second derivative, since it's bending downward, is negative. So going from smallest to biggest, it would be the second derivative, then the function itself, and then the first derivative. So that would be d. An equation of the tangent line to the graph of this at the point 0, 1. Notice that this is a y-intercept, 0, 1, so we just need to find the slope here. So let's see, the derivative of that would be 1 plus derivative of cosine is minus sine of x. Plugging the 0 in here, the sine of 0 is 0, so the slope would be 1. So that looks like it's going to be the line y equals 1x plus 1, which is b. Number 19. If this is the second derivative of a function, then it has inflection points when x is equal to. Might have seen this one before too. Notice that this here, because this factor is getting squared, if we set up the number line here with negative 1, 0, and 2, it's not going to change signs of the 2 because that factor is getting squared. So what you're going to find is it changes it here and here. I'll let you fill out those numbers for the number line. You can test the points, but it's going to be negative 1 and 0 only. What are the values of k for which the area under this from negative 3 k is equal to 0? Well, let's just do the antiderivative and see what happens. Antiderivative of this is x cubed over 3 from negative 3 to k. We want that to be 0. That's k cubed over 3 minus negative 3 cubed over 3. We want that to be equal to 0. Well, the only way that's going to happen is if k is also negative 3, right? And of course, negative 3 does make it 0. If you think about the graph, you could think about this graphically too. The graph of this function looks like this. So we want to know where is the area from negative 3 to some other value k. Well, this is all positive. So you can't ever get this area to be 0 unless you just go from negative 3 to 3, right? It never goes down, so you never have a chance of getting negative area to cancel out. So only negative 3 to 3 works. Number 21. Okay, this is one of the ones that you could do this by working backwards, I think. We don't actually know how to do this yet because there's a y over here. We don't know how to take antiderivatives where there's a y over here. This is like the antiderivative version of implicit differentiation. And we'll learn how to do that later. But we could, anyway, try to figure out, just by taking derivatives of these, which one could be right. So let's see if we can do that. 2e, what would the derivative of this be? It would be 2 times e to the k t y times the derivative of what's inside, which is, like, now t is like the x and y is like that, so it's going to have some chain rule. This is going to be too complicated. It's not going to be the right one. Let me try to get you right to the right answer here. Let me do this one. It's b. I believe b is the right answer. So what's the derivative of this? dy dt would be 2 and then let's see, the k, I would be 2e to the kt times the derivative of what's inside. T is the variable like the x here, and this is just a number, so the derivative of what's inside would be that. And then here, that would actually be, since this is y, it is actually k times y. So that's the right answer. If you figured that out, that's great. If you didn't get that one, I wouldn't worry about that because we really haven't done that yet. I'm just going to work backwards to get it. Number 22. The function f is given by this. On which of the following intervals is f increasing? So we find increasing and decreasing intervals by examining the derivative. 4x cubed plus 2x, and we set that equal to 0. And I'll do a little factoring here. Looks like we take a 2x out. So we need 2x squared plus 1. And that's equal to 0 at 0. This is not equal to 0 anywhere. If you set up the equation, you're going to get something with an I in it. So that's the only point on our number line that we need to consider. And then plugging numbers in here, we find that when I plug in positive numbers, it's positive, and when I plug in negative numbers, it's negative. And that means it's increasing from 0 to infinity. These numbers, if you're wondering where these things came from, that would be if you solved this and made some kind of sign mistake and you lost the I that's going to be in there. But if you think about this, since x squared is always positive, 2 times that is positive plus 1, this can never be equal to 0. Okay, number 23, the graph of f is shown in the figure above. Which one of the following could be the graph of the derivative of this? Well, let's see. Here's a place where the derivative would be 0. So it's got to cross the x-axis. So I think these two are out, right? Based on that. And it's increasing or positive here and then decreasing. So it's positive and then negative. So this would be a candidate. This is backwards. And this is positive and negative. But notice that this is a straight line. A straight line would be the derivative of a quadratic or a parabola, and it's not a parabola, so that leaves us with this. Okay, so that could be the derivative. Last page. I think we've seen this one before. The maximum acceleration. That means I need to find, if I'm looking for the maximum of something, then I need to find the derivative of that thing and set it equal to 0 and do the number line. So if this is velocity, then acceleration would be 3t squared minus 6t plus 12. And the derivative of acceleration, which is, since we're looking for maximum acceleration, would be 6t minus 6. And that's equal to 0 at 1. So setting up my number line and plugging numbers in, I find that when this is like 0, for example, this is negative and that's positive. So the maximum acceleration happens at t equals 1. But they didn't ask for at what time. They asked what is the maximum acceleration. So I need to plug 1 back into my acceleration function. So that would be 3 times 1 minus 6 times 1 plus 12. That's 3, that's 9. Oh, but, hold on, hold the phone. But they give a closed interval here, so we actually have to test the endpoints too. So we have to test 0, 1, and 3. We just found at 1 it's 9, but we also need to find the endpoints, right? Because I could have a bigger maximum. So plugging 0 into my acceleration function, I get 12, so already that's bigger than 9. And plugging 3 in, I get 3 times 3 squared minus 6 times 3 plus 12. That's 27 minus 18 is 9, plus, so that's 21. So that's actually the maximum acceleration. I almost forgot to check the endpoints. Number 25, what's the area of the region between the graphs of this and this? This is a little bit of a stretch. We haven't quite done this, but I think you could figure this out if you sketch a little graph. So let's see. The area between two things. So y equals x squared from 0 to 2 looks like this. That's a piece of the parabola. We could find that area. And then y equals negative x, that's this line. That's like a triangle. So the area between these two, okay, we'll learn that the area between, we're talking about geometric area here. This is a shape, right? So the area between these two curves is the positive versions of these areas. So the area under this would be the antiderivative from 0 to 2, which would be 8/3. And then the area of this is a 2 by 2 triangle. So that area is, let's see, 2 times 2, 1/2 base times height would be 2. Adding those gives me 14/3. Number 26, if the function f is continuous from 0 to 2 and has these values from this table, then the equation f of x equals 1/2, which is a horizontal line, or setting that, sorry, that's where our function intersects the horizontal line, 1/2, must have at least two solutions if k is equal to, well, let's draw a picture here and see if we can figure out what this is about. The point 0, 1 is on it, and the point 2, 2 is on it. And we're trying to get it to intersect, we're trying to get our f of x function to intersect this line twice. Well, if we want to make sure it does that, then I think we've got to make it dip below that line. If it dips below and comes back up, and it's continuous, right, so it can't jump over the line, then I think k would have to be some number less than 1/2. And the only one is 0. If k was 1/2, then it would have at least one solution. But if you want to make sure it crosses that line twice, it's got to dip below there. So that would be A. 27, skip average value of a function. We don't know how to do that yet. And number 28, if f of x is equal to, okay, we can do that. The derivative of tangent 2x would be secant squared of 2x times the derivative of what's inside. And let's see, at pi over 6, that would be secant squared of 2 times pi over 6 is pi over 3 times 2. That's 1 over the cosine of pi over 3 squared times 2. The cosine of pi over 3, that's the x-coordinate pi over 3, that's 1/2. 1/2 squared is 1/4. 1 over 1/4 is 4, times 2 is 8. So I think all the possible answers, if you forgot that answer is there. If you mixed up your sine and cosine, or you forgot to multiply this by 2, those answers are there, so be careful. Okay.